Hello everyone, this is Nusrat Jahan Nipi.
And this is Aisha Nehar Choudhury. Today we are going to discuss about a problem. The problem is finding Walrasian demand for the CES utility function. The problem belongs to a course called Advanced Microeconomics from Chapter 2 entitled Utility and Demand. So we are starting with the problem. So the problem number 2.1 is finding Walrasian demand for the constant elasticity of substitution utility function. Consider a consumer of CES utility function. The function is given below, where the coefficient rho satisfies that rho is not equal to 0 and rho is less than or equal to 1. Problem number A is find the Walrasian demands of this consumer. X1 is a function of PW and X2 is a function of PW. So let's start with this solution of problem A.
Okay, Aisha, let's go to the solution. So, we need to find the Walrasian demands of this consumer, X1 and X2. So, first we have to Lagrange this individual utility maximization problem, which is, we can see in the screen that L of X1, X2, lambda equals to X1 to the power rho plus X to the power rho whole to the power 1 by rho plus lambda into W minus P1 X1 minus P2 X2. Here, lambda is the Lagrangian operator, P is the price level, and W is the wealth level, and W minus P1 X1 minus P2 X2 is the budget constant, and X1 to the power rho plus X to the power rho whole to the power 1 by rho is the utility level. So, taking the first order conditions yields that the partial differentiation of differentiation of the Lagrangian function by x1, x2, and lambda yields that x1 yields that x1 to the power rho plus x to the power rho whole to the power 1 minus rho divided by rho into x1 to the power rho minus 1 minus lambda p1 equals to 0. And then with the x2, it yields x1 to the power rho plus x to the power rho whole to the power 1 minus rho by rho into x to the power rho minus 1 minus lambda p2 equals to 1. Then with lambda, it yields w minus p1 x1 minus p2 x2 equals to 0. Coming to the next slide, we see that rearranging the first two equalities, we obtain x2 is equal to x1 into p2 by p1 to the power rho minus 1. And plugging this result into the budget constraint, we obtain that p1 x1 minus p2 into x1 into p2 by p1 whole to the power 1 by rho minus 1 equals to w or wealth level. And solving for x1, we find the Walrasian demand for good 1 is x1 equals to w into p1 to the power 1 by rho minus 1 divided by p1 whole to the power rho by rho minus 1 plus p2 whole to the power rho by rho minus 1. Coming to the next slide.
Stop. Hold on a second. Hold on a second.
Okay.
I think their P is like denoted for price. Okay. Is it right?
Yes.
Okay. I got it.
Okay. So coming to the next slide, we see that for compactness, we express the demand as x1 equals to w into p1 r minus 1. Here, this r equals to the rho divided by rho minus 1. As we can see, it is for the compactness, and as well as p1 to the power r plus p to the power r. And then we can finally plug x1 into x2 in order to find the Walrasian demand of the good 2, and hence we find x2 is equal to w into p to the power r minus 1 divided by p1 to the power r plus p to the power r. So here is the end of the solution of question B. And can you please read the next question?
Okay. We already have completed the solution for question number A. Now we are moving forward to solution of B. The question B is, what is the Walrasian demand of any good I is equal to 1, 2 when parameter P tends to 0? Sorry, parameter rho tends to 0.
Okay. So when the parameter rho tends to 0, it can be said that the consumer's preferences can be represented with a Cobb-Douglas utility function. So if it tends to 0, rho tends to 0, then the parameter R also approaches to 0. In this setting, the consumer's Walrasian demand for good I is xi pw equals to w into pi to the power r minus 1 divided by pi to the power r plus pj to the power r. And it becomes, we can see that in the next slide, it becomes limit of r tends to 0, xi equals to w into pi to the power minus 1 divided by 1 plus 1. Then it equals to w by 2 pi, which exactly coincides with the Walrasian demand of consumer with Cobb-Douglas utility function. And can you, we are at the end of the question B. Can you describe the question C?
Okay. We have already seen the solution for question number B. Now we are moving forward to question number C. So question number C is, now consider a variant of the above CES as the following function and show that the question number I of C is when rho is equal to 1, rho is the parameter. So when the parameter is equal to 1, indifference curves becomes linear. That means goods 1 and 2 are perfect substitutes.
Okay. So for this question, we have that rho equals to 1. Then u x1 x2 equals to alpha 1 x1 plus alpha 2 x2. Then the utility function becomes linear as the goods are perfectly substitutes. The equation of an indifference curves can be obtained by solving for x2. Hence, the x2 equals to u by alpha 2 minus alpha 1 by alpha 2 into x1. For instance, for u equals to 10, the linear difference of the curve originates at 10 by alpha 1 and crosses the crosses the x1 axis at 0 equal to crosses the x1 axis at 0 equal to 10 by alpha 2 minus alpha 1 by alpha 2 at x1 equals to 10 by alpha 2. So
Okay.
in the next slide, we can see that that question is solved, and we come to the next question. Now, where p tends to 0 and it represents the Cobb-Douglas utility function of u of x1 x2 equals to x1 to the power alpha 1 into x to the power alpha 2, where the exponents satisfy alpha 1 plus alpha 2 equals to 1. Let us define u tilde of x equals to ln u of x, where ln u of x equals to 1 by rho ln a1 x1 to the power rho plus alpha 2, sorry, it was alpha 1 x1 to the power rho plus alpha 2 x to the power. Then the limit of this utility function when the p tends to 0 is limit of rho tends to 0, u tilde of x equals to limit of rho tends to 0 into ln alpha 1 x1 to the power rho plus alpha 2 x to the power rho divided by rho equals to 0 by 0. So in the case of 0, we have to use the L'Hopital's rule as follows. Limit of rho tends to 0. Differentiation of ln alpha 1 x1 to the power rho plus alpha 2 x to the power rho of d of rho divided by d of rho by d of rho equals to limit of rho tends to 0 and hence the differentiation it goes on to this final result, and it is x1 to the power alpha 1 into x to the power alpha 2 divided by alpha 1 plus alpha 2. Recall that so far
It's a
we have
long
been,
equation.
yeah, it's very long, but we have to use this L'Hopital's rule to extend it somehow to understand this whole problem. So we can recall that so far we have been dealing with the limit of rho tends to 0 u tilde of x, while in fact we are interested in limit of rho tends to 0 u of x. So given that u tilde of x which equals to the ln u of x, we have that limit of rho tends to 0 u tilde of x equals to x1 alpha x1 to the power alpha 1 into x to the power alpha 2. Solving for x2 yields the equation of an indifference curve x2 equals to q tilde divided by x1 to the power alpha 1 whole to the power 1 by alpha 2. And hence, if we consider alpha 1 is equal to alpha 2 equals to 0.5, the indifference curves becomes x2 is equal to u tilde 2 divided by x1. Hence, the difference curves are increasing in x1 but at a decreasing rate. So we can see that indifference curves are bowed in towards the origin, and that was what our question needed to be solved. So, Aisha, can you describe the third question?
Yes, sure. So here we can see the question 3 of the problem set C. So when the parameter p tends to 0, the utility function becomes a lengthy utility function of u into x1, x2 is equal to mean x1, x2, and thus represents two moods that are perfectly complements. So we need to show that if x1 is greater than equal to x2 is greater than equal to x1, then what happens?
Okay, Aisha, some of your voice was cut because of the internet connection. So I will try to cover that in my next speeches. So here we need to show that if x2 is equal or more preferable than x1, then limit of p tends to infinity, negative infinity, then alpha 1 x1 to the power rho plus alpha 2 x to the power rho whole to the power 1 by rho equals to minimum of x1 x2 equals to 1. Suppose without loss of generality that x2 is more preferable or equal to x1, then x to the power rho is less or equally preferable to x1. Since parameter rho satisfied,
Okay.
0 doesn't equal rho is less than or greater 1 and approaches the negative infinity as it is a negative number. Hence, multiplying both sides of the inequality by alpha 2, which is greater than or equal 0, yields alpha 2 x to the power rho less than or equal alpha 2 x1 to the power rho. Adding alpha 1 x1 to the power rho both sides of this inequality, we get the following equation, and rearranging it further, we get this following equation. In the last equation, we added the power of 1 by rho simultaneously on both sides. And in addition, if x1 is greater than or equal 0 and x2 is greater than or equal 0, then 0 is less than or equal alpha 2 x to the power rho. Then we add alpha 1 x1 to the power rho on both sides of the inequality. We obtain alpha 1 x1 to the power rho, which is less preferable or equal to alpha 1 x1 to the power rho plus alpha 2 x to the power rho. So coming to the next slide, now we say that since rho is a negative number, it becomes a bit like this equation, and combining this result with that of expression 1 yields this equation. So this following equation, we need to use the squeezing theorem to obtain the limits of terms A and C, where rho tends to the negative infinity, and in order to obtain the limit of term B, which must be between A and C, now we need to first find the limit term of A. So in this case, limit of rho tends to minus infinity, which is alpha 1 x1 to the power rho whole to the power 1 by rho equals to x1. Now let us find the limit of term C. So in this term, we see that we use alpha 1 plus alpha 2 into x1 to the power rho whole to the power 1 by rho, which again equals to x1. Coming to the next slide, we see that both terms A and C coincide, and both of them are x1. So the limit of B must also be x1. That is, we can see that in this equation, the limit of B is also x1, which is exactly what we needed to show if x2 is more preferable or equal to x1, and then the limit of alpha 1 x1 to the power rho plus alpha 2 x to the power rho whole to the power 1 by rho equals to the minimum of x1 x2, which equals to x1. A similar argument applies to the case in which x2 is less than x1, whereby alpha 1 x1 to the power rho plus alpha 2 x to the power rho whole to the power 1 by rho of limit case equals to the minimum of x1 x2 equals to x2. This isn't related to our question, but we can also derive it, so we showed it here, and hence our questions and the solutions ends. And Aisha, if you have any question, please feel free to ask.
Thank you so much, Nusrat. Well, you can move forward to the next slide, please.
Okay. So thank you all for watching, and if you have any queries, please comment below. And thank you, Aisha, for companioning me here with this slide and the video, all this. And thank you. Now let's end this. Okay?
I also want to show my gratitude towards you that you discussed the question so easily. I understood the solution of the problem so well, and I hope that the audience will understand as well. So thank you everyone for watching, and if you have any queries, please comment below. Bye.
Bye.